Welcome to today's Explainer. Today, we're skipping the high-level tech news and going straight back to basics. We're going to decode the fundamental blueprint of modern computing, literally from the ground up. And when I say from the ground up, I really mean it. We're pulling this knowledge straight from the source. Dense, rigorous university study notes and actual exam papers on computer organization and architecture. Now, don't worry, you absolutely won't need a number 2 pencil for this. We're taking those complex, intimidating pages and distilling them down into a totally engaging crash course to give you absolute clarity on how computers actually work. So here is our syllabus for today. 1. Digital versus analog computers. 2. Architecture versus organization. 3. The von Neumann blueprints. And 4. Core components and functions. Section 1. Digital versus analog computers. Okay, let's start with the broadest categories of computing. You've got digital on one side and analog on the other. The digital computer, which is almost certainly what you're using to watch this explainer, works with discrete data. We're talking strictly zeros and ones. It relies heavily on memory units, and because of that binary nature, it's highly accurate. Analog, on the other hand, is a totally different beast. It works with continuous physical data, things like voltage or temperature. Because it deals with the messy real world, it's generally less accurate due to noise, and it usually doesn't even have memory. It relies entirely on its physical circuit configuration. For our journey today, we're going to be zooming in completely on the digital side. Moving right along to Section 2, Architecture versus Organization. Now, these two terms get thrown around a lot, and they sound super similar, right? But to a computer scientist, they mean very different things. Think of it kind of like building a house. Computer architecture is your logical floor plan. It describes exactly what the computer does. It's the functional behavior that a programmer actually sees, like instruction sets and data types. Computer organization, though, that describes how it actually pulls it off. This is the physical plumbing, the wiring, the structural units, circuit designs, and adders. So architecture dictates the logical capabilities, while organization dictates the actual physical performance. To really wrap our heads around this, let's look at the instruction set architecture, or the ISA. The ISA is basically the ultimate example of architecture over organization. It represents all the attributes of a computer system that are entirely visible to the programmer, the things that directly affect the logical execution of a program. It's this critical bridge that connects your software instructions to the hardware's capabilities. It explicitly defines the instruction formats, the opcodes, and the available registers. Think of it as the core algorithm for controlling instruction execution, completely regardless of how those physical circuits are organized behind the scenes. All right, Section 3, the von Neumann blueprint. Let's travel back to 1946. A brilliant guy named John von Neumann proposed an absolutely revolutionary idea called the stored program concept. Before this, computers were these massive, rigid machines that had to be physically rewired to run different programs. Von Neumann's stroke of genius was to store both the data and the instructions in the exact same memory space. It elegantly simplified everything. Suddenly, machines could be reprogrammed dynamically just by changing the software in that shared memory. It was a total game changer. If you actually map out this architecture, you can see how brilliant the flow is. On one side, you have the main memory, which is where those instructions and data live together. Sitting right in the center is the central processing unit, and that's broken down into the arithmetic logic unit for doing the math, and the program control unit, which acts kind of like a traffic cop, directing everything. Then, on the other side, you've got your input and output equipment. It creates this incredibly dynamic, beautifully efficient closed loop of information passing back and forth. Section 4, Core Components and Functions. Let's look under the hood. So, a single processor computer system really consists of 4 major structural components. You can think of them as the major organs of the machine. First up is the central processing unit, the CPU. This is the brain. It controls the operation of the computer and performs data processing, housing that arithmetic logic unit, the control unit, and some temporary storage called registers. Second is the main memory, which holds the data and program instructions that are currently in use. Third is the input-output, which is responsible for transferring data between the computer and the outside world. And fourth, tying the whole shebang together, is the system interconnection. These are the communication paths that actually connect the CPU, the memory, and the I/O so they can talk to each other. Okay, so we've got our organs, we've got our physical parts listed out. But a pile of parts doesn't make a functioning computer, right? So I want you to ask yourself, how do these static components actually operate together in real time? What is the core behavior here? Well, according to our source material, it all boils down to four basic functions. Number one, data processing. The computer has to perform arithmetic and logical operations on data, which is mostly handled by the ALU. Number two, data storage. It has to store data, either temporarily in registers while it's working or permanently in memory devices. Number three, data movement. The system has to constantly shuttle data back and forth between internal components or out to external I/O devices. And finally, number four, control. The control unit has to manage the operation of all these different pieces and dictate the step-by-step execution of the instructions: processing, storage, movement, and control. If a machine can do those four things under the von Neumann architecture, congratulations, you've got a computer. And that brings us to the end of our explainer. We've taken these incredibly dense academic concepts and built a clear, structured view of digital architecture, all resting on a foundational design proposed right after World War II. But it does leave us with a pretty fascinating final thought. As our modern demands for massive data processing, artificial intelligence, and complex parallel computing just continue to explode, will we ever truly outgrow John von Neumann's Junius 1946 blueprint? Or is that stored program concept going to remain the beating heart of technology forever? Thank you so much for joining me today, and I really hope this gave you the foundational blueprint you were looking for.